Welcome to this first session, which is a sort of warm-up session, not a technical one. I don't plan to be very long, a bit less than 1 hour, in order to have some minutes for some exchanges, questions, and so on. Let me firstly say that I'm glad to be here at ENAC, because I have several friends and colleagues here. Also, I give some lectures at the Master 2 level. I still give some lectures. Actually, I would say that when I accepted the invitation, it was months and months ago, and I didn't realize that I was still on vacation, on holidays. But I was on holidays in Biarritz, on the Basque Coast, so I was glad to fly away from Biarritz this weekend. You know why. So, the key character of this talk is Fermat. But I will deliver my talk in a broader perspective. The region where we are, the time, the 17th century, the collective memories nowadays, and of course, a bit of mathematics also. I will not have time to propose you some open problems for the coming weeks. So let me begin by where we are. You arrived this morning probably by car, by bus, maybe by subway, and when you got out from the subway, you see an announcement like this, the quartier, Rangueil, where we are, the announcement of the University Sabatier, which is part of the organizing committee here. Actually, Paul Sabatier was a chemist who won a Nobel Prize in 1912, and the main university on science and medicine, took the name of Paul Sabatier exactly 50 years ago in November 1969. I mention that because for some of our students, actually is not Paul Sabatier, but Patrick Sabatier, who is a television presenter. And from time to time, I've read, well, I have studied at the university, Patrick Sabatier. But, well, this is one of our Nobel Prize winners. But let me mention also two others. Another not in chemistry, but in physics. And it's interesting because he was born exactly in the same administrative division, in the same canton than Paul Sabatier, Albert Fert, who is another Nobel Prize winner some years ago. And of course, the most recent one in economy, Jean Tirole. Well, I say that the main character of the talk will be Fermat. So maybe you could ask, how do you pronounce it? Fermat? Fermat? Like you say from some places, Muret, Fermat in the local language. Also, you could ask Fermat or Pierre de FERMAT with this particule. Let me immediately say that both are correct, Pierre Fermat and Pierre de FERMAT. And I will explain why. He was born Pierre Fermat, he died Pierre de FERMAT. First enigma, where was he born? Almost everywhere you will see he was born in 1601. Now we are sure that this is wrong. He was born, we are sure, between 1601 and 1610. And now historians are pretty much sure that he was born in 1605. It doesn't matter very much, but this is a sort of new contribution on this enigma. The reason for that is that there were several Pierre Fermat who were born about the same time in the same family. It's not completely clear, but that was the first enigma, and many people wrote about that. For sure, he died in 1665, for sure. He died in Castres, in a town which is not very far from here, 1 hour driving. Anyway, if you want to see the birthplace of Fermat, you could. I will show you. But if you want to see the grave or the tomb of Fermat, you couldn't. Because the rest of his body in Castres were transferred probably to Toulouse, but there is no place where you could go and say, well, this is the place where Fermat was buried. Some picture. Here are some portraits. We use the one on the left mainly because we are almost sure of that. Of course, he's a person of the 17th century. And with this portrait, you have this one, which is in a special place in the capital, the so-called capital, in the town hall of Toulouse. You can go and visit. It is at the first floor. It's open to visit. And that's a beautiful place called Salle des Illustres. And there you will find this buste, this statue of Fermat. With mentioning Fermat mathematician, which doesn't mean anything because mathematician at the 17th century doesn't mean anything. There was no mathematician at the 17th century. You also find in the same place this statue here, with mentioning here somewhere, well, the legend is Fermat and his muse. Fermat and his muse. Some colleagues say Fermat and his PhD student. Well, that's and mentioning here Fermat, inventeur du calcul différentiel, which is a bit exaggerated, but anyway. For a long time, I gave lectures on differential calculus. I like very much this topic. And when students were not very easy at that point, I would say, well, go and say Fermat that he invented the differential calculus. So you can see this statue in the same place, Salle des Illustres. Where did he live? This is what I call the triangle of life of Fermat. Firstly, he was born close to Castel-Sarrazin in a region called Tarn-et-Garonne, which is at about 1 hour driving from here, where there is still the place where he was born, the house, the tower where he went, and so on. Most of his professional life was in Toulouse, but also partly at the end in Castres, Tarn, where he died. So let's say that mainly, essentially, he lived in this triangle. He went out of this triangle 2 cases. Firstly, a bit to Orléans to study law, and some months to go to Bordeaux for professional reasons. But let's say that his life was in this triangle. And finally, he got out from his triangle by his genius. So you can go out of your space by your writings, by your sayings, by your scientific production. His motto, aime à être inconnu. He was a very discreet person. He said, well, firstly, I will explain that he was mainly a lawyer, a counselor of the Toulouse Parliament. So his profession was to be conseiller au Parlement de Toulouse. So during the work sessions, he was in Toulouse, and during holidays, he went back to Beaumont. How? With his carrosse, or also on the river Garonne. And he did mathematics. He was not a mathematician, he did mathematics during holiday time. And he was complaining, I don't have enough time for my mathematics. Also, he didn't like to write down things, like some colleagues. to prove things, but when you have proved something, well, let's go to another point, okay? And he used to say, I'm a lazy person. But the way of doing science, I will explain later, and to do mathematics in some provocative way, announcing things, I'm able to prove that. Let us see if you are able. And of course, the other guy said, well, what is okay? Likes to be unknown. Before going further, some general references. First one, it's a video we have concocted some years ago. This one is in French, but with some English subtitles. It will be proposed on a screen outside. It's 24 minutes long, not too long, and explain what happens with Fermat, and especially what happens after the death of Fermat, to produce papers or to copy papers of Fermat by his son. But if you look, of course, it is already in YouTube, because if you are not in YouTube, you don't exist now. You know, paper, books don't exist anymore. You have to be on YouTube. Okay? Well, so it is on YouTube, but in French. But you will have the video with English subtitles outside. But if you decided to watch this video, I will counsel to read first the description of the sequences. I will let some copies outside, but it is 24 minutes long. Another reference, the most recent one, is this one, which has been sponsored by the university and some local publisher, Pierre de FERMAT, enigmatic, but actually it concerns not really science, it concerns history of that period, the Parliament of Toulouse, and the law, and so on. Science appears, let's say, for 15% of the book. But this is the latest book on the subject, and I would say the most accurate on the date of birth, on the work of Fermat, and so on. So the publisher have provided some copies here. Just some copies, so if you are interested, I could sell you 18 euros, and if you are also, if you like to, that me sign it, I will be pleased to do that. This one is less than, it has been published in December last year. It's really this kind of work, much more technical. 300 pages on the contribution of Fermat to the beginnings of geometry, of analytical geometry. I know that some of you are very much interested in that area. That's why I put this reference, which is a very recent book, but a really technical one. I mean, technical one on geometry. And finally, if you want to know a bit more about the history of science, this is the explanation of the book. You see, the book aims to fill this gap and to provide a benchmark study devoted to the entire geometrical work of Fermat. And he explains and so on. And the author is not only a mathematician, but he is mainly an historian. But he is really technical. Well, you have to love geometry, to go inside, to see exactly. The book is in the library of Math Institute. Okay. Now, if you're just interested by the history of science, I like this booklet. It is quite a recent one by a Canadian sociologist. And he explained in, let's say, less than 150 pages the history of science as a general topic, especially the one of 17th century. And I mention that because I like this kind of book, light in weight and price. Well, let us speak of the 17th century. The 17th century is a very specific one. It's a pivot century. It's the century where some physical notions have been made mathematics. That's a century of mathematization of some real things. Of course, some roots or principles of physics were known. Velocity, acceleration. But these notions have been made mathematics. And as you know, that's a century when has been devised the derivative, first derivative and so on, with many big names. Many big names. I will mention some of them. Let me just begin with the trio I like, Descartes, Pascal, Fermat. Three big names, related. I will mention them, but also many other names. What did it mean at that time to do mathematics? First, to be a teacher. Well, to be a teacher, clear. To teach something, some commercial rules and so on. But astronomer, mathematics were made for astronomy, navigation, and ballistics. The important was to go on war, to win wars. So imagine a publication like this today. L'art de jeter les bombes. The art of throwing bombs. You see that the trajectory is not really parabolic, but okay. Or here. So it was, I would say, somehow specific century, and roughly, quickly said, this is also a century of wars, guerre de religion, of epidemics, very tough century, and fortunately, at least in the area here, the century ended with a beautiful construction at the end of the century, the so-called Canal du Midi. It was built at the end of the 17th century, and the Canal du Midi is at some hectometers from here, which goes from Toulouse to the Mediterranean Sea. And the Canal du Midi has been built rather quickly in 15 years. In 15 years for this huge construction. The contribution of Fermat. Let's say that it can be divided in three parts. It's usually divided in three parts. Analysis and analytical geometry. You know that Fermat used to say, he assessed some statements like la nature agit par les voies les plus courtes ou les plus économiques. So nature chooses the shortest of the optimal or the most economical way of doing. This is a sort of variational principle, I would say that. He didn't design exactly the derivative, but he was able to use the derivative. I could explain afterwards how. He was able to use the derivative and to say that as some local extremum, for example, this notion, not defined notion called the derivative, had to be zero. Formally, the derivative has been set and defined by Newton, Leibniz, but only some years later. And Newton acknowledged what Fermat did. So I would say the first part, sort of variational principle, or the beginning of differential calculus. That's why the statement was put in the Salle des Illustres. The second one is the roots of analytical geometry with Descartes. They never met. They used to send letters. And Fermat always sent letters in a provocative way. And Descartes got angry. He was furious. And I would say that he didn't believe that Fermat actually proved things. He used to say, Fermat est un Gascon, pas moi. It means that Fermat is someone from the southwest, but not like me. But finally, at least for the physical notion of refraction, they both converged to the same things. The approaches were different, but actually there is no opposition between them. Of course, Descartes is better known, he is also a philosopher. But really, between Descartes and Fermat, there has been a fight, arguments, and so on. The third part is the beginnings of probability. You are more concerned about that with Pascal, Blaise Pascal, the son. They exchanged a lot of letters. They had mutual admiration. And even they planned to meet somewhere in France between Clermont-Ferrand, where Pascal was, and Beaumont, where Fermat was, in the middle somewhere, Aurillac. And finally, they never met, and they died almost the same year. So this trio, again, Descartes, Fermat, Pascal. And finally, probably the topic for which Fermat is best known, the number theory. The number theory because of what? Fermat was a very erudite person, was able to speak several languages. I don't know Occitan, but probably, but several languages. Of course, Latin to communicate, but also Greek. He was able to write poems in Greek. And he was able to study also the structure of languages. He was a philologist. But he used to read books on number theory from the past, mainly the books by Diophante. And not only he read these books, but when reading, he proposed results, he conjectured many results on number theory. And probably that he is mainly known for his number in number theory. A word on how people used to work at that time. Of course, there was no internet. The main way of communicating was to send mails. But mails you see, in these trunks. In French, we say la malle-poste. And I mention malle-poste because it has given the English name mail. Mail comes from mal. And it seems that worked. In a certain sense, for sure, it was possible to send a letter from Toulouse to the Netherlands, and if you got the answer immediately, to have the answer back in 3 weeks, which is not so bad. And everywhere in Europe, they exchanged it by letters. There was no academy centralizing, collecting works. The Academy of Science in Paris was created in 67, just some years after the one in Toulouse, which is the first one. But during the period of Fermat, there was no academy. And there was a guy who played really a key role in Paris, and this guy was Mersenne, le père Marin de Mersenne. And Mersenne was, his role consisted in collecting all the contributions from everywhere in Europe, copying them, not photocopying, copying them, and distributed them to everyone. He played a key role. So that's why probably there is a center, a mathematical center now in Paris called Mersenne Center. And he was called at that time or later le secrétaire des savants en Europe for diffusing. But I would say the main way of working was exchanging letters. And they sent many letters. Here is a map of Europe. Of course, you recognize some big names. Not locally, maybe if you know Lalubert, Mignon, but for example in Italy, Cavalieri, Galileo, Torricelli. In the Netherlands, Descartes was there at that time, Huygens, Snell, Van Schooten, Christine de Suède, in England also. He exchanged it a lot with English colleagues, especially Digby and Wallis. Wallis is one of integrals. You remember this exercise is Wallis integrals. And in France, of course, you recognize the names I mentioned. Pascal, but not only, Roberval, Cassendi, and so on. So that was the way of working at that time. Now, let me go a bit deeper in mathematics. And I would like to show you 3 examples of contribution of Fermat in mathematics, and I have chosen number theory. And I have chosen examples which are not so well known. Of course, I will speak of the famous conjecture at the end, but something else. Let me begin by this one doesn't work, the other one works. Okay. 26, the number 26. What can be said about the number 26? I can say that it is squeezed, coincé, between 25 and 27. Until that you follow. Okay? But 25 is a square, the power. 27 is a cube. So 26 is squeezed between a cube and a square. Okay? Fermat claims that's the only case among all the integers. How did his brains work? How were his neural connections? He is a lawyer. So in mathematical terms, that means that the equation x squared minus u minus y cubed equals plus or minus 1 between squares and cube. The only case is 26. And that's true. You can prove that. Among all the integers, the only integer squeezed between a square and a cube is 26. I don't say following powers, between 2 powers like this. It's 26. And he was very proud of that. He was very proud of that, saying in letters, well, I'm able to prove that. Let us see if our English colleagues are able. Well, I was angry. Okay. That's the first example, a very simple one. The second example I like very much is the one concerning, well, this one. The first time I gave this talk was in 2017, so I have to adapt today. What about 2017? It's a prime number, but it's also the sum of 2 squares. 2017 can be written as the sum of 2 squares of integer in an unique way. You have 10 minutes to find the decomposition. Okay? But I mentioned 2018 because it is not a prime number, but it's 2 times 1009, and 1009 is again a prime number which can be written as the sum of 2 squares. You have 15 minutes for the answer. Well, I don't say anything about this here. But I mentioned that because Fermat wrote the following letter. It was Christmas. He wrote a letter. A prime number is a sum of 2 squares of integer if and only if it is of the form k times something plus 1. Characterization. And he wrote that in a letter during a Christmas evening. That's why this result is called Fermat's Christmas gift. And this is true. The proof is not so easy. If you try to prove that any prime number is a sum of the square of 2 integers, if and only if it is of the form k times 4 times something plus 1. You see that 2070 is 4 times 200 something plus 1. le théorème des deux carrés de Fermat, ou le cadeau de Noël de Fermat. How did he imagine that? He's a lawyer. He said, yes, I have a proof of that. Well, actually, he didn't have a proof of that. And we had to wait Euler 150 years later to have a formal proof. But anyway, Fermat conjectured. He says this is true. This was my second example, and I have to go to the main, of course, the main equation. I have put here on the slide, and on the right part, you see this, you see this painting. And this painting in the right, you can find it and see it downtown in Toulouse. Downtown in Toulouse, there is a place called Place du Capitole, where is a town hall, and there is a series of paintings on the ceiling of arcades with the main facts or the main points related to Toulouse. And well, there is this equation. You will find this, and you see here, maybe not clearly, but you see this famous equation. Of course, the equation was known for a long time since Pythagoras for n equal to 2, and we know not only this equation has integer solutions, but we know that we know all the solutions. So what Fermat said and wrote in a copy of the book by Diophante, let us fix now n any other power, 3, 4, 5, any other. If you look for solutions which are integers, that's impossible to find solutions. There is no solution. No, of course not non-zero solutions. So when the power is 3, 4, and so on, there is no solution. That was a statement. But what was more provocative was what he wrote later. Well, it's impossible, but I have a marvelous proof, but I have no place in the margin to write it down. So you see the provocative way. Well, this is true, but I have a marvelous proof. This margin is too narrow, and he wrote it down. So imagine people reading after him. Did he have a proof or not? He claims that. He was able to prove, he proved it in another place for n equals 3. And of course, you know the story of many mathematicians afterwards proved it 4, 5, and finally, you know, the final proof by Andrew Wiles and Taylor in 1995. But that was, I would say, even if he didn't have a proof, he was able to state the result. How did he see that when n was greater than 3, it was impossible to have solutions? So this is a famous equation, maybe one of the most famous equations in number theory, even if it is solved now. And certainly, he is the equation who detains the world record of wrong proofs. Thousands of wrong proofs. Maybe some of you receive from time to time proofs. I have myself a box of wrong proofs in my office. I don't even open proposals. I mean, but because at least when someone proposes a proof, you should see in the proof the difference between n, 2, and the others. Because for n equals 2, there are solutions. You didn't even see the proof, so there is a okay. It continues. It has been proved, but it continues. I'm sure that the Academy of Science still receive proofs of this thing. Well, the statement was very, very, very simple to understand. That's why the equation was so famous that it can be seen in the capital, downtown in Toulouse, when you go. Okay. Well, as I say, just parenthesis for an amusement. You know that it is generalization, what's called, everybody who knows, all the pupils in our schools know, Pythagoras theorem. We say Pythagoras, but it was known long before Pythagoras. Pythagoras' case was when n equals 2. Just let me mention the following one. I like very much when you are in a dinner with friends on a lunch. I don't ask you for calculation. You have a rope of 100 meters. Okay, 100 meters. You just add 1 meter. So the new rope is 101 meters. That means that you can a bit pull up here the rope. The rope is fixed here, okay? Question asked around you during a dinner or lunch, what is h? I don't ask for calculation. Of course, you are able to calculate it via Pythagoras, but just your intuition. What should be h? 1 meter? No. It should be less than 1 meter, of course. More? Less? The answer is more than 7 meters. More than 7 meters. Of course, it's easy calculation with Pythagoras, but nobody around you on the table will answer more than 7 meters. So I explain again, you have 100 meters, you just add 1 meter, you pull up the rope, the h is more than 7 meters. A house could be put. So even the Pythagoras theorem could provide some surprises. The simplest one. Well, just to mention that because I like this example. And of course, I proposed it several times, and nobody proposed the correct answer. Now, of course, you could provide the correct answer by saying that you are applying a Pythagoras theorem. It's not complicated at all, but it is surprising. And mathematics could be surprising. Some appreciation by Carcavie concerning Fermat. He was one of the highest genius of our century. Or Pascal, who was really an admirer of Fermat. You are in Europe the one I consider as the most important geometer. Now let me go now to the last part of my talk to show with some pictures some reminiscences or at least the collective memory, how Fermat is in the collective memory and news nowadays. This is the place, the birthplace of Fermat in Beaumont-de-Lomagne. This is exactly the same, that was the house where he was born, with a tower. And this is a place where there is a statue of Fermat, but what's interesting is that in statue, around the statue, you have some quotation by Laplace, Cauchy, Pascal. So you are at about 1 hour from here, completely in the countryside. And of course, in Beaumont-de-Lomagne, what's important is not mathematics, it's garlic. Garlic and horses. But in this statue, you have statements by Cauchy, Laplace, and so on. The guy who is here, you have recognized Andrew White, who visited this place when he got the Fermat Prize some years ago. And it's interesting because when he went to this place, Andrew White's, the visit was very well prepared, and all the peasants were around him. They knew that someone important was coming to Beaumont concerning Fermat, and I remember very well this guy asking White in French, "Alors, Monsieur Willis, il est démontré votre théorème?" It was really a great moment. To have this. Okay. This is a statue at Beaumont-de-Lomagne in bronze. For example, I mentioned here a statement by Laplace. Okay. This is a birthplace of Fermat, and there is now we have a project since years to have its building transformed in sort of museum of mathematics and computer science. It's a long project. We have all the plans and so on. There is just one thing missing: money. But we still hope that now in 2 years we will be able to open this Maison Natale de Fermat, devoted to mathematics and computer science, or science in general. So this is modern application of differential calculus. Some other memories, because people have written on that, of course, books, videos, one by Singh. There is even a movie in Spanish, very interesting movie, and the characters were Hilbert and Poincaré and so on. You have the objective of in the movie was with professional. You are in a room and you have to solve some conjectures. And if you don't succeed, the walls are coming to you, to crushing you. So you have to solve them. And finally, with the help of Hilbert, they finally solved. Well, that's the history of the movie. This one is a famous one, with some mistakes, but a very successful book. And let me just finish by my last slide with this aspect. There is a company in France, Orange, devoted to telecommunications, and they have this habit of giving names of scientists to their boats. This one was launched quite recently, 2014. Just before was launched a boat named Descartes. And when this, the first day when this boat was launched, he had to go to the sea for rescuing another boat. And the other boat was Descartes. This is a true story. Well, let me just finish by some references. First one, some popularization. The history of differential calculus to variational calculus from Fermat to nowadays. In a journal, yes, for everyone, Quadrature. Most recent one on some open problems coding curves. The videos that I mentioned, and 2 videos in English, which can be seen in YouTube. Well, my purpose was to propose you an open problem. I don't know, we'll have time. You have time? Okay, just 3 minutes, because you cannot go out from here without any new problem to solve. This is the following problem. Oh, well, let me explain. This is kind of problem, find the shortest curve such that, etc. All the problems are of this kind, including the papers that I mentioned. Find the shortest curve that satisfies such and such property. The problem I'm going to mention is solved in 2 dimensions, but it's not solved, it's open in 3 dimensions. So you have 3 or 4 days to solve it. The problem is the following one. Let me put it firstly in words. You are in the sea, and you know you are at 1 kilometer from the seaside, but you are in the fog. Your instruments tell you you are at 1 kilometer from the seaside. What is the shortest path to follow to be sure that you meet the seaside? In other words, you are in the forest looking for mushrooms. You have let your car on the street, on some road, and you have to go back, but you don't know in what direction. You know you are at 1 kilometer from the road, but you don't know where the road is. So what is the shortest path to follow to be sure that you meet these roads? In mathematical terms, what does it mean? You live, let me see here, you are at 1 kilometer from some tangent line. So what is the shortest path leaving the center 0 to be sure that you meet, when I say meet, that means even touch, cross, all the tangent lines to the circle. So the first naive attempt would be to say, okay, I go 1 kilometer and I say this. I'm sure to meet all of them. I posed this problem to some young engineers, including Airbus, because when they have lunch, they like to solve some problems. And they came back with some other solutions, like this one. You leave, etc. And you be sure that this curve is shorter and it meets all the tangent lines to the circle. Even better, this one. You leave the center and you meet all the tangent lines you can check to the circle. Well, it is shorter, but is it the shortest? Not only you have to announce it is the shortest, but you have to prove it. And we have the proof. This is the shortest. This is shortest. I mean, you leave the center, you go like this, and this curve in orange, you are sure that it meets all the tangent lines to the circle. But for this one, it has been proved that it is the shortest. I don't like very much the proof. For geometrical consideration and so on, and dividing, I would have preferred a proof with calculus of variation or optimal control. I know the result, but I have no proof. Well, in that case, so the question is, what about the same problem in 3 dimensions? You have to leave the center of the sphere and to follow some trajectory such that the trajectory meets all the tangent plane to the Earth. We have some proposals. I have the record proposed by some, even from people from Airbus contributed. I see Thierry here. But we don't know if it is the shortest, and because I have no proof. We have only contributions. So, when I posed the problem in a writing, a colleague came back, not by the solution, but as usual in mathematics, by proposing another problem. And it's an interesting problem because it has to do with, you see the environment where we live, satellites and so on. This is a dual problem, which is the following one. What is the shortest curve above the Earth from which you can see any point on the Earth? Imagine you want to monitor the Earth, surveiller, your satellite or something, follow some curve, and you are sure that from that curve you see any point on the Earth. Some connecting curve. I have no idea of the proof. I have no idea. You can give proposals, of course, but proposal, but not shortest path, no proofs. I think that's all, and I still have maybe a couple of minutes for answer the question. Thank you very much for your attention.